Hey Patrick, how are you?
Hey, how's it?
Good. All right, let's wait a couple of minutes to see if someone else joins, and then we can start.
So, how was New York?
That's very cool. Yeah,
Yeah,
really nice. Really, really
I
nice.
guess you've been there a couple times.
No, this was my first time.
Oh, okay.
So, yeah, lots of new stuff, lots of cool stuff.
Yeah,
Yeah.
I haven't been to New York too many times myself.
Mhm.
I I grew up more West Coast side, but
That's nice.
I went to it recently. It was pretty cool. It was pretty
Mhm.
amazing. Big
Yeah,
town.
yeah, yeah. Let me share the link also in Discord.
So let me see. Oh, yeah. Um,
So weird. Discord is not working on my laptop. Just one sec. Okay, let's start. First, share my screen. So, Discord thingy. So the idea for today is to discuss chapter 7, which is about fine tuning. And Patrick will take the lead there. Um, oops, Discord is opening. Uh, I want to apologize for last week. My flight changed, and then I realized that if that based on the change, I wouldn't have been able to make it. And I told Mash um, to host the previous week, but I didn't. I expected that I was gonna be able to host last week, and I couldn't. So yeah, sorry about that. And also thanks for Mash for moderating 2 weeks ago. But yeah, that's about it. So Patrick, if you want, you can take it from here.
okay, great. Let me share my screen.
Mhm.
Oops. Host disabled attendees sharing screen.
Let me
So
change that. Let me check again.
let me
Current
try again.
settings. Yeah, you can do it now.
Okay. Uh, Okay, I think I got it.
Nice.
Huh. They're sharing you.
Mm-hmm.
Let me
I see.
see. Um, let's see. That 1 second. Okay, so let me get my slides up. Can you see the slides yet?
Yes, I can see it.
Okay, great. Okay. Look, so today we're gonna do fine tuning. Specifically, we're gonna do Chapter 7, Fine Tuning AI Engineering by Chip Huyen. So it's we're gonna do it, but I just would like to draw attention to the fact that recently Sebastian Raska released two YouTube presentations on fine tuning for his, I believe it was chapter 6 and chapter 7. They're great resources, and I already finished the number 6, and I'm about to start number 7. So they're just released and they're fantastic. So onward now to the AI Engineering Chapter 7, Fine Tuning by Chip Huyen. Okay, fine tuning is the process of adapting a model to a specific task by further training the whole model or part of the model. And fine tuning adapts a model by adjusting its weights. Uh, it is most often used to improve the model's instruction following ability. Because when you first make a foundational model, basically, or as the trend as the term is now used, when you make when you get or make a foundational model, it's going to be really adept at usually the next word sequence kind of thing. It does have some fine tuning, but you can do fine tuning yourself for certain problems. For example, if you wanted to do um, classification, and you want to get a definite answer, yes, no, is it spam or not spam, you can train a large language model to be excellent at a very specific task, and then it gives you great value in using it as an application. Okay, so fine tuning adapts the model by adjusting the weights, and it is most often used to improve the model's instruction following ability. And it can improve the model's domain specific capacities, such as coding or medical question answer. So sometimes it can also improve the domain specific capacities because you're extending or adding to its current encyclopedic kind of domain. You're adding a subset of specialized data with, specific answers so that it knows a little bit more about a specific subject and how to treat it. So let's see, fine tuning. Compared to prompt based methods, fine tuning incurs a higher memory footprint. At the scale of today's foundation models, naive fine tuning often requires more memory than that's available on a single GPU. This makes fine tuning expensive and challenging to do. Okay, so fine tuning overview. To fine tune, you start with a base model that has some, but not all, of the capacities you need. The goal of fine tuning is to get this model to perform well enough for your specific task. So, a specific task, you could have, like an assistant, it's going to be like your voicemail assistant in an application, and you'd have like what's that, Twilio answering the phone line, and then you got your message prompt, and it could actually speak. Whatever your application is, and so sometimes you got to fine tune it. But oftentimes it's very difficult and challenging to do. But still, it's very important to understand all these nuts and bolts so that you have a better understanding of the whole the whole you know industry of the whole lay of the land. You have to have the complete background. I would love to try to do fine tuning. I haven't done it yet, but I have been studying it, so I think eventually I'll be doing it. So, at any rate, let's see right here. Fine tuning overview continued. Fine tuning is one way to do transfer learning. Transfer learning focuses on how to transfer the knowledge gained from one task to accelerate learning for a new related task. So, very good examples coming up here. And early large scale success in transfer learning was Google's multilingual translation system. The model transferred its knowledge of Portuguese English and English Spanish translations to directly Portuguese Spanish. So it went from, it had a knowledge base that understood how to basically translate between Portuguese English and English Spanish, but it didn't have the ability to do Portuguese to Spanish. Okay, so even though there were no such examples, they were able to train the model with the two existing knowledge bases of Portuguese English and English Spanish. They were able to do transfer learning, and we were able to build up a system of Portuguese Spanish. So that just shows you how amazing this technology can be. Since the early days of deep learning, transfer learning has often offered a solution for tasks with limited or expensive training data. So sometimes the training data is extremely expensive and difficult to curate or create. By training the base model on tasks with abundant data, you can then transfer that knowledge to a target task. And that's exactly what they did with the multilingual example. So for LLMs, knowledge gained from pre-training on a text completion, a task with abundant data, is transferred to more specialized tasks like legal question answer or text to SQL, which often have less available data. So, using this technique of fine tuning, they're able to really improve essentially the way these models can respond to new tasks. Ideally, much of what the model needs to learn is already present in the base model. And fine tuning just refines the model's behavior. OpenAI's Instruct GPT paper in 2022 suggested viewing fine tuning as unlocking the capacities of a model all that a model already has, but has difficulty for users that are difficult for users to access via prompting alone. So the base model has certain capacities, but users are having a difficult time accessing that good data, that richness of capacities. And so fine tuning can unlock or make available uh, that by connecting the dots. So Again, the fine tuning isn't the only way to do transfer learning. Well, I start again, but fine tuning is not the only way to do transfer learning. Another approach is feature based transfer. Feature based transfer is very common in computer vision. A general purpose model that performs well on a wide range of benchmarks might not perform well on your specific task if the model you want to use hasn't sufficiently been trained on your task. Fine tuning it with your data can be especially helpful. Okay, up to slide 11. Reasons to fine tune. If you just if you just if you're just starting to experiment with a project, fine tuning is really the first thing you should attempt. So that's pretty good guidance. You'd probably want to be doing prompting out initially. Fine tuning requires high upfront investments and continual maintenance. So that's something to consider. Uh, First, you need data. Annotated data can be slow and expensive to acquire manually. Uh, so again, reasons to fine tuning as we get further reasons here. AI engineering experiments should start with prompting and then explore more advanced solutions only if prompting proves inadequate. However, the number of examples you should use with a prompt is still limited by the maximum context length. With fine tuning, there is no limit. So that's an important caveat. And so you can only paste so much into uh, the context space for a given prompt. When you're doing prompting, and so you want to paste in all the errors and say, hey, wow, how to fix this code. Maybe you got so much context that it's too much, and so you wouldn't be able to do it. So likewise, if you can't solve your problem with prompting because it's beginning to become too big, and it's something that it could be solved better with fine tuning, then sometimes that's the way you have to approach the problem. So once you've maximized the performance gains from prompting, you might wonder whether to do RAG or fine tuning next. If the model fails because it lacks information, a RAG system that gives the model access to the relevant sources of information can help. Uh, the paper, Fine Tuning or Retrieval by Ovadia et al. I don't know if I pronounced his or her name correctly, but in any case, uh, demonstrated that the tasks that require up-to-date information, such as questions about current events, RAG outperformed fine-tuned models. So that's important to know. You naturally have to read the paper. So I've included the URLs. You can click on most of these, so you can actually check out the sources more easily. Uh, on the other hand, if a model has behavioral issues, fine tuning might help. So if it's acting odd and it's not like following your instructions or trying to do the kind of application specific task that you're envisioning, then maybe fine tuning is what you need. And so in that sense, it's behavioral, and you gotta fix the issue so that it behaves the way you want it. Okay, so fine tuning and RAG again. And so if a model has behavioral issues, fine tuning might help. One behavior issue is when the model's outputs are factually correct but irrelevant to the task. Okay. Uh, there was an example offhand. I forget that example, but that's an important thing. I mean, so you could have factually correct things coming back, but if it's not solving the specific task, application specific task you want, then that's where fine tuning can help. Fine tuning the model with well defined technical specifications can make outputs more relevant. So, fine tuning can get things back on track so that those factual outputs are relevant to the task you're trying to solve. Another issue is when it fails to follow the expected format. For example, um, you requested HTML output, but you got text or JSON instead, or vice versa. If it doesn't follow through and provide the output that is expected and specified, that's a behavioral issue that you can repair or fix with fine tuning. Naturally, you'd want to first start with prompting and make sure that that's really the issue. But if it's lacking, for example, the fundamental syntax of JSON, it might not follow through, as an example. And so, like, let's say your base foundational model lacks certain concepts, of how to parse and display HTML or JSON. Unlikely, but you got a specific foundational model that was made a certain way, and it lacks certain things. It doesn't have everything. So you might find for your specific task, it doesn't have that, training for that concept. And you've got to now use fine tuning to build up instructional follow through ability so that it follows what you want it to do. All right. So semantic parsing is a category of tasks whose success hinges on the model's ability to generate outputs in the expected format and therefore often require fine tuning. As a reminder, semantic parsing means converting natural language into a structured format like JSON. It's not just unstructured text, for example. It has a specific meaningful semantic, semantics means meaning. So the structure conveys meaning because of the way it's parsed up. Like this is a company slash company. Well, that's XML, but you got the dictionary like tag of company, and then the quoted text following it. So it's giving it semantic meaning by guiding how things, so if you want to define a person, you get a name, date of birth, etc. And so you'll have tags and text next to each thing, like as a dictionary kind of layout, and that's sort of like the way JSON is. And so this is important. Semantic parsing might need fine tuning if it's not behaving correctly, depending on what you're trying to do. Now, I think most foundational models are going to support JSON, HTML, etc. But you may have a very specific application and you're doing something new. And so you have to train the model so that it understands what you need it to do. Okay, so if your model has both information and behavior issues, start with RAG. Okay, and so RAG is a typically easier to do since you won't have to worry about curating training data. Well, that's certainly easier. And when doing RAG, start with the simple term-based solutions such as BM25 instead of jumping straight into something that requires vector databases. I think that's a good idea. However, if you've been doing databases forever, it's not that much It's not that hard to play with vector databases. It just depends on your background. I think that's a good statement for people that are getting started with AI, generally speaking. But if you have a lot of background with databases, I don't think you necessarily have to have a term-based solution. The simpler, term-based rather than the more complicated embedding with the vectors databases. There's so many great tutorials and websites and prototypes out there for vector databases. I don't think anybody with good programming skills is not going to have troubles uh, with vector databases. But for someone new, absolutely, that was good advice. And sometimes you can solve things the simple way. You don't always have to have the whole kitchen sink. Sometimes it's a heavier solution, and sometimes it's better to do a simple solution. And you should understand how to do things more than one way, and you don't always need to do it in a complicated way. So fine tuning the workflow to adapt a model to a task. Okay, so we're going to talk about a workflow to adapt a model to a task. Try to get a model to perform your task with prompting alone, and then add examples to the prompt. You can tell the prompt 5 things, and then you can show 3 examples. By showing examples, it helps your AI program understand what to do more readily. It's got some examples. It gives it better context of how it should behave. If your model frequently fails due to missing information connected to data sources such as RAG. And so I'm not quoting the book directly, but almost all of these things are um, like usually 95% or more quotes from the book. Occasionally I'll paraphrase a few things, but most of it's pretty straightforward from the book. Start with basic term-based search. Build and test. If the model continues having info-based failures, you might want to try even more advanced RAG methods such as embedding-based retrieval. For continued behavioral, I should probably say behavioral issues, but behavior issues, opt for fine tuning and combine RAG and fine tuning for even more performance boost. Okay, so that's pretty general. I wouldn't get too caught up into that one. It's just general advice. So next, several slides are going to be on memory bottlenecks. Because fine tuning is memory intensive, many fine tuning techniques aim to minimize their memory footprints. Memory needed for fine tuning is typically much higher than the memory needed for inference because of the way neural networks are trained. And so, to continue, the key contributors to a model's memory footprint during tuning are its number of parameters, its number of trainable parameters, and its numerical representations. You can reduce memory requirements for fine tuning by reducing the number of trainable parameters. And reducing the number of trainable parameters is the motivation for PEFT, or parameter efficient fine tuning. Okay, so now we're going to get into back propagation and training parameters. A key factor that determines a model's memory footprint during fine tuning is its number of trainable parameters. The memory needed for each trainable parameter results from the way a model is trained, and neural networks are typically trained using a mechanism called back propagation. So if you've been getting into AI and large language models, back propagation is already probably, you're probably well versed in the idea, generally speaking. So with back propagation, each training step consists of two phases. A forward pass, the process of computing the output from the input. Okay, so the forward pass is the process of computing the output from the input, and the backward pass is the process of updating model weights using the aggregated signals from the forward pass. So during the inference, only the forward pass is executed, while during training, both passes are executed. So it's a little bit more onerous or taxing with training uh, because you are doing both forward and backward pass. At a high level, backward pass works as follows. Compare the computed output from the forward pass against the expected output, the ground truth that that's like the answer to a truth. I mean, a question is called the ground truth, and so you calculate it, and then you compare it to the the ground truth that's already been when the question was added. They'll mark they'll have a question and they'll answer it. So the ground truth is what it should be. If they are different, the model has made a mistake and the parameters need to be adjusted. The difference between computed output and the expected output is called the loss. And so that loss is used to adjust the weights. So compute how much each trainable parameter contributes to the mistake. This value is called a gradient. Mathematically, gradients are computed by taking the derivative of the loss with respect to each trainable parameter. There's one gradient value per trainable parameter. If the parameter has a high gradient, it's significantly contributes to the loss and should be adjusted more. Okay, so if it's got a high gradient value, then you're gonna have to adjust that parameter more based on that high gradient to make it closer to what's expected. All right, so adjust trainable parameter values using their corresponding gradient, which we just touched on. How much each parameter should be readjusted given its gradient value is determined by the optimizer. Common optimizers include SGD, the scholastic gradient descent, and ADAM. For transformer-based models, ADAM is by far the most widely used optimizer. And then we'll get in a little bit to the back of memory needed for inference, or maybe, yeah. It's useful to know how much memory a model needs so that you can use the right hardware for it. You might need to calculate whether you can run a certain model in terms of its memory requirements. If a model requires 30 gigabytes of memory to do inference, a chip with 24 gigabytes of memory won't suffice. During inference, only forward pass is executed, as we noted, which requires memory for the model's weights. So let N be the model's parameter count, and let M be the memory needed for each parameter. the memory needed to load a model's parameters is n times m. Okay, so we'll get into specific examples soon enough with that. The forward pass also requires memory for activation values. Transformer models need memory for key value vectors for the attention mechanism. The memory for both activation values and key value vectors grow linearly with sequence length and batch size. Okay, so Chip just mentioned that there were other things needed for memory, even just for the forward pass part, such as activation values and key value vectors for attention mechanism. And then it's stated here, for many applications, the memory activation and key value vectors can be assumed to be about 20% of the memory for the model's weights. For example, n times m times 1.2. So, for example, consider a 13 billion parameter model. If each parameter requires 2 bytes, the model's weights will require 13 billion times 2 bytes equals 26 gigabytes. The total memory for inference will be 26 gigabytes times 1.2 for the overhead, which will equal 31.2 gigabytes. And overall, the memory needed for training is calculated as, so more generally, the memory would be calculated like this. Training memory is equal to model weights plus activizations plus gradients plus optimizer states. And so for another good example, imagine you're updating all the parameters in a 13 billion parameter model using Atom Optimizer. Because each trainable parameter has 3 values for its gradient and optimizer states, if it takes 2 bytes to store each value, the memory needed for gradients and optimizer states will be 13 billion times 2 times 3, or rather 3 times 2 bytes, equal to 78 gigabytes. All right, so very general. I'm sure that the math could get a lot heavier. That's just pretty easy to conceptualize. In the memory calculations so far, I've assumed that each value takes up 2 bytes of memory. The memory required to represent each value in the model contributes directly to the model's overall memory footprint. If you reduce the memory needed for each value by half, the memory needed for the model's weights is also reduced by half. And then we're going to move to memory numerical representations, which can have a big impact on the memory footprint. Before discussing how to reduce memory needed for each value, it's useful to understand numerical representations. So numerical values in neural networks are typically values represented as floats. And the most common family of floating point formats is the FP family, which adheres to the Institute of Electrical and Electronics Engineers, the IEEE standard. Okay, so what's used commonly in AI, in the AI world, are floating point formats, but you'll see soon that sometimes they use integers too. There's a reason, but integers don't hold as much precision. So sometimes there's advantages either way. So sometimes you have to do it one way or the other. So this gets a quicker overview on a more specific overview per IEEE 754 standard. There are the FP32, the FP64, and the FP16. So obviously FP16 is 16 bits, 2 bytes. The FP32, 32 bits, 4 bytes. That makes sense. And FP64 is the largest float at 64 bytes, total of 8 bytes. Okay, it's called double precision. So obviously, probably the earliest like 10 years ago, they were probably using FP64 a lot. And then I think today the standard is often FP32 and sometimes certainly FP16, as we will see. Quantization or quantization, however you pronounce it. We'll get to that in a second. Okay, so any rate, while FP64 is still used in many computations as of this writing, FP64 is the default format, for example, for NumPy and Pandas. So it's definitely used for many tools that you'll be using. It's rarely used in neural networks itself because its memory footprint is too big. Okay, so FP32 and FP16 are much more common. Other popular floating point formats in AI workloads include BF16, BFloat16. I'm unaware of that standard offhand, and the TF32, TensorFloat32. Obviously, that's Google's standard. Numbers can also be represented as integers such as int8 and int4. And anyone that's done programming is going to know that those kind of things right away. Certainly if you do a little bit of C programming. Okay, quantization. Quantization is a concept that deals with where you're simplifying the precision. You're going to lose a lot of the fat, if you will, and so you're left with the skinny. So the idea of quantization is you can reduce the memory footprint, but not lose the important intelligence that you've built up. So you try to lose the fat and keep the skinny. That's basically it. But I should check. I mean, if anyone has any questions at this point, please let me know. If you want to contribute any idea or point. I don't want to just wax on without checking how you guys are doing.
All good from my side. I don't know if anybody else has any question.
Okay,
well, that means yeah, no, sorry, continue.
Okay, I'm just making sure. All right, so quantization. This is not quantum, by the way. It's not quantum computing. The first bits needed to represent models' values lower. I'm losing the context here. The fewer bits needed to represent a model's values, the lower the model's footprints. Okay, so a 10 billion parameter model in a 32-bit format requires 40 gigabytes for its weights, but the same model in 16-bit format will only require 20 gigabytes. So it's all about how big it is, but obviously smaller floats aren't going to provide as much precision. So you have to have good quantization that does it very intelligently, that loses the fat and keeps the essential core training and task-based instructions that you've built up. Reducing precision, also known as quantization, is cheap and extremely effective way to reduce a model's memory footprint. And obviously, if you're going to do and get into fine tuning, you'll be very concerned about this because you could literally run out of memory as you're fine tuning a large project. Low precision generally refers to any format with fewer bits than the standard FP32. Ideally, you want to quantize whatever is consuming most of your memory, but it also depends on what you quantize without hurting performance too much. And weight quantization is more common than activization quantization. So it's usually weight quantization, since weight activization tends to have a more stable impact on performance with less accuracy loss. Um, this section focuses on memory efficient fine tuning techniques, which center around parameter efficient fine tuning. Okay, and so we're going to get more into parameter efficient fine tuning in just a second. Fine tuning tailors one model to specific needs. Model merging combines multiple models, often fine tuned models, for the same purpose. So you can do fine tuning of a single model, and then you can also merge or combine fine tuned models, usually for the same purpose. Okay, so parameter efficient fine tuning. In the early days of fine tuning, models were small enough that people could fine tune entire models. This approach is called uh, full fine tuning. Okay, and in full fine tuning, the number of trainable parameters is exactly the same as the number of parameters. Full fine tuning can look similar to training, uh, but the difference is that training starts with randomized model weights, whereas fine tuning starts with the model weights that you have previously trained. All right, so consider a 7 billion parameter model. If you use 16-bit format FP16, loading the model's weights alone requires 14 gigabytes of memory. So, wow, there you go. Fine-tuning this model with Atom, also a 16-bit format, requires an additional 7 billion times 3 times 2 bytes for a total of 42 gigabytes of memory. So you're going to have to add that. The total memory needed for the model's weights, gradients, and optimizer states is then 14 gigabytes plus 42 gigabytes for a total of 56 gigabytes. But 56 gigabytes exceeds the memory capacity of most consumer GPUs. So it's all about being able to calculate your requirements ahead of time, knowing how much memory it would take and what your hardware requirements can support. Due to high memory and data requirements of full fine-tuning, people started doing partial fine-tuning. In partial fine-tuning, only some of the model parameters are updated. While partial fine-tuning can reduce the memory footprint, it's parameter inefficient. However, my only concern about that particular statement was there wasn't a good example to explain parameter inefficient, although it kind of alluded to in the next couple of paragraphs. Anyone has a comment about that? Otherwise, no worries. You'll see. Parameter fine-tuning requires many trainable parameters to achieve close to that of full fine-tuning. Oh, okay. So a full fine tuning. You need to update approximately 25% of the parameters to achieve a parameter comparable to that of full fine tuning on the glue benchmark. So I think it's something about that. You still need a lot of parameters, so it's parameter inefficient. I guess I'm not sure. Anyway, it's not that important. All right, so we just keep on going. So here again, we're focusing in on parameter efficient fine tuning, and the idea of PEFT, parameter efficient fine tuning, was introduced by Housley et al. In 2019, where the authors, and I'll quote that paper in a couple slides, showed that by inserting additional parameters into the model in the right places, you can achieve strong fine tuning performance using only a small number of trainable parameters. So that's that's certainly an example of where you didn't need too many. So it's because you're using this parameter efficient fine tuning strategy. On the glue benchmark, they achieved a performance of 0.4% of the full fine tuning using only 3% of the number of trainable parameters. So that's a pretty good technique. However, the downside of this approach is that it increases the inference latency of the fine tuned model. And PEFT enables fine tuning on more affordable hardware. So that's probably sometimes makes it very popular. Okay, so I included a little flow chart, and you'll see charts. I've never been a big fan of flow charts. I think they're more of a heuristic, heuristic. You know, it gives you a general idea of something, and but oftentimes flow charts they're more creative. They, I just included it because it looked cool. All right, so the PEFT techniques. Sometimes a flow chart is very good. I'm not saying that flow charts are always bad, but oftentimes it's more eye candy than anything else. The existing prolific world of PEFT generally falls into two buckets: adapter based methods and soft prompt based methods. Adapter based methods refer to all methods that involve additional module that involve adding essentially additional modules to the model weights, such as the one developed by Hosley et al. And Laura, which it was spearheaded by a paper by Hugh et al. In 2021, is by far the most popular adapter-based model. So we'll be talking about Laura in just a second. If the adapter-based methods add trainable parameters to the model's architecture, soft prompt-based methods modify how the model processes the input by introducing special trainable tokens. These additional tokens are fed into the model alongside input tokens. Soft prompts are continuous vectors resembling embedding vectors and are not human readable. It was definitely not. Woo. Soft prompts can be optimized to backpropagation using the tuning process, allowing them to adjust for specific tasks. So I can't tell you I know all the niceties of all these different techniques, but you don't have to. You're just picking up the general lay of the land, and it's obviously as you get into certain projects, you'd have enough of the vocabulary and general knowledge of how things are for certain issues, and you just have to bone up and study more on a particular issue that could solve your problem. So this is where I got the quote, the citations all quoted if you're interested in following them, but they're provided in the original book as well. Unlike the original adapter method by Houseby in 2019 et al., the Laura low rank adaptation, which is Hugh et al. In 2021, incorporates additional parameters in a way that doesn't incur extra inference latency. Okay, that's why I think Laura became very popular, because you obviously don't always want that extra inference latency. Instead of introducing additional layers to the base model, LoRa uses modules that can be merged back to the original layers. You can apply LoRa to individual weight matrices. Given a weight matrix, LoRa decomposes this matrix into the product of two smaller matrices, then updates these two smaller matrices before merging them back to the original matrix. Okay, and so we get into a little bit of the details, but not much really, because it's a long chapter, and we're actually almost done with it. And Laura looks fascinating, but it was, like I said, a very long chapter. So I got a little bit tired at the end, but I did a good job. I can't. So consider the weight matrix W of the dimension n times m. LoRa works as follows. First, choose the dimension of the smaller matrices. Let R be the chosen value. Construct two matrices. A, which would be one of the matrices, dimension n times R. Oh, okay. I see construct two matrices. So I guess, well, let me just follow it. A, m times R, their product is W8 AB, which is the same as W. Okay. I'd have to review that a little bit more. Why doesn't read?
Maybe what is missing there is the dimension of the matrix B. Right?
Yeah,
Which will be like R times M, I guess.
Yeah, I think I'm missing something there. R is the low rank thing. So yeah, somehow I think I gotta review that again. But at any rate, if we go to the next slide, I think it's right here. Ultimately, this is the equation that they're gonna build up. So you got, I don't know why they add the hat to A there, but that's just stylistic notation. So you got W plus R over 2 over R, and you times that to WAB. Well, it's got a little tick mark right there, and that means because of this over here. Anyway, like I said, I was getting tired of that point. So I think, Laura, it would be worth a lot more to review it if you were going to get into fine tuning with current transformer models. Definitely, you would want to check it out. Okay, so then it's just a little bit more, fine tuning. Update only the parameters in A and B. W is kept intact, blah, blah, blah. It's like this basic recipe. But I think also that it wasn't as well presented. So it's hard to pull it together in a compelling way, because it's just sort of a quick recipe. So I can't build it up better than it is, because I would have to use other information sources to make it a little bit more interesting, and I was running out of time. So at any rate, what are you at the end? Because then, it looks like I got duplicate slide there. So I will delete that one. So then I actually ended with the as additional material, because it's right about, it's doing exactly what we're talking about, fine tuning, and it's more hands-on code-based examples by Sebastian Roska. So it looks it's excellent. So chapter 6 of his book is classification, and chapter 7, which is instruction fine-tuning, he just released that within the last 24 hours. And I'm just about to start that one. And his book is also superb. So,
Nice.
so fine-tuning is definitely interesting stuff. And I'm getting into it from all different sources. And but I think mostly what you're going to probably be doing is you're gonna nowadays, unless you're actually fine-tuning models, you'll probably, like it says, you'll start with prompting. So when you first start designing, and also if you're doing, and nowadays a lot of the programming is more agent-based and MCP servers and that kind of stuff.
Nice. Thanks, Patrick. Very well explained. Yeah. Does anybody has any question? I see.
Hi, Naveen. Yeah. So just a basic question. I was wondering, based on the overview that was provided, like in LoRa and even Clora, that only a small percentage of the parameters are chosen to train. I was just wondering, on what basis are they chosen? Given there's so many parameters. Anyone has any a take on that or any insight on that?
I'm not sure. Can you, Santiago? Can you reiterate the question so that maybe I can? My hearing is something's bad.
Yeah, I think Naveen was saying like, okay, the LoRa adaptation uses a smaller percentage of parameters, and so Naveen's asking like, how do we choose these ones? Like, right, Naveen? Like
Yeah.
how?
Yeah, I just pasted the question in the chat as well. Like on what basis are the parameters to be trained chosen? Like in fine tuning, not all the parameters are trained. Only select parameters are trained. Like if there are 100 parameters, then I understand, let's say 95% parameters are kept the same, but only 5% are kind of tweaked or fine-tuned. So how do we, on what basis is it chosen that, these 95% won't be disturbed, these 5% will actually, we will do the tweaking in there. Yeah, I was just wondering.
Well, I'm not sure because I just got into the LoRa stuff, but there is that paper that is, let me check where it's on slide 46. What I would do is probably want to read up on the fine tuning or retrieval. It's a paper with Ovadia and a bunch of others. It's so
I can look that up.
I think that's you'd have to review the details because I'm new to LoRa as well, so I haven't actually read the paper.
Yeah, I mean we're all learning.
Yeah,
anyone has an take. Yeah.
Thanks. My understanding is that we actually we cannot say, hey, let's keep these ones frozen. Let's change only these specifically. We can say things about the percentage, and the percentage we can say it based on the rank on this R. So basically, if this R is big enough, it's the same as pre-training all the weights. But if this R is small, then we just affect the smaller percentage. But your question is good because then it's we cannot control which ones are we gonna affect, but I mean we will affect. I don't know, Carlos.
I only used LoRa once and it was only in a course, so I'm not an expert. But what we were doing back then was to take a model that was big And when we're using LoRa, the idea is that if you have a matrix that is that you want to fine tune, rather than, let's imagine that I'm going to use very tiny numbers so we can have them in our head, but let's imagine that you have a transformer that has a 5 × 5 matrix. That means it has 25 parameters. With LoRa, the idea is that you can get only 10 parameters because you have 2 vectors of 5 × 1. That's more or less the idea. You don't have to stick to those numbers, but the idea is that you are going to keep the original values. You're normally not going to override them, so that 25 parameters are still going to be there, and then you're going to add this matrix that is multiplication that you create on another side. So at the end, the final model is going to have 25 plus the 10 additional parameters that you're training. So that, apart from that, I think that there is another question that is nabbing what you're asking, which is you can do this for what part of the model?
Yeah, yeah.
It's only the final layer or something like that. I think this is independent. This is a technique for training some layer, but then you have to choose what layers, if it's all the model or just a part of it.
Okay, okay, interesting. Yeah, that's helpful to know, Carlos. Thanks.
Yeah. Any other questions? No? Oh, good. Then thanks, Patrick. Before we go, let me also ask if there's anybody that would like to tackle chapter 8, which is dataset engineering, something new that we didn't, like some of this stuff we cover as well on practical side with Sebastian's book, but dataset engineering, I think we didn't. Kind of interesting. Any volunteer? No. All right, that's great. I can ask in Discord, and if
Yeah,
not, then
maybe
I'll take it.
it's gonna be a busy week. Yeah, maybe let's float it in Discord.
Yeah. All right. All right. Again, Patrick, thanks for an amazing
Thanks,
presentation.
Patrick. Yeah,
Very well explained.
Thank you.
Yeah, I hope you all enjoy and see you next Sunday. Bye.
Aloha.
Aloha.
Thanks.